Good afternoon, class. In today's video, what I'd like to do is to follow up on what I did in the previous video about energy and to go through what we call conservation of energy, especially when it comes to things like escape velocity and getting rockets into orbit, like in the International Space Station that I used in the last video. So for this one, to talk about conservation of energy, what you have to understand is that we always talk about it in terms of keeping energies balanced. So if there's kinetic energy, there is potential energy. And so the sum total of the change in energy in the total environment is zero. There's no change in the energy, it's just going from one form to another. Should sound familiar about the normal laws of conservation of energy that you learned back in elementary school. So, given that case, we said kinetic energy is equal to potential energy, and in this case I'm using gravitational potential energy. And so what I did was I wrote down those equations, the formulas for kinetic energy and potential energy, and then I set them equal to each other, and then I did a bunch of math. So in this case what I did was I said, okay, I'm going to go through, in this video I'm going to go through all of the different, the variable manipulations in order to get the result. And the reason that's important is because I want you to understand what the mechanics are and what factors really matter when it comes to escape velocity. And for those of you who stick around to the end, there's the extreme case that I talked about in the last video as well. So here we go. So we set 1/2 mv squared for kinetic energy and mgh for gravitational potential energy. However, now what we have here is we've got m on one side and m on the other. So long as the mass is not zero, we can actually divide this out. And this is in general true for everything with mass. So it's a good assumption we can divide both of these out. So we're left with 1/2 v squared equals gh. At which point we're trying to isolate the variable. So in order to isolate the variable, we need to do the opposite operation that's being done to it so that it can stand alone. So in this case, we've got 1/2 v squared. So what we're going to need to do is multiply both sides of the equation by 2 because 1/2 is dividing it. So we've now got v squared equals 2gh, and then now the operation being done to the velocity is the square function. So the opposite operation of the square function is the square root function. So we take the square root of both sides of the equation and we get v equals the square root of 2gh. Which is great. And if you're doing this in like if you were just taking a ball and dropping it off of a cliff, this equation right here, you could use that. Feel free. It works very well, especially if you want to determine the height of the cliff. However, this makes the assumption that you know what gravitational acceleration on that planet is, or that celestial body is. So if you don't know that, what you need, but you have like the mass and the radius of the planet, then you can actually do this, but you're going to have to reformulate this. So that's why I wrote this part here. So in this case, we're going to let h equal the distance from the center of gravity of that object. So in this case, it's going to be the center of the Earth. And we're going to let that equal to r. Okay? You'll see why in a little bit. It kind of doesn't matter. It's just that I wanted to make it distinct from, height is distinct from the distance from the center of of gravity. So just so that we're clear on why I set it the way I set it up this way. So also I'm going to let g equal the lowercase g equal gm over r squared, which hopefully you remember from the gravitational forces equation. This would have been the same as F equals g m1 m2 over r squared. The only difference is that instead of force, I use mass times gravity, and then the first mass cancels out because they're on both sides of the equation. So v, when I substitute my g and my h back into here, what I get is that v equals 2 uppercase capital G mr over r squared. Now, of course, we can simplify this. So when we do, because these r's are the same, v is equal to 2gm over r. And where m is the mass of the Earth, or the whatever planet you're on, and r is the radius of the planet that you're on, whether it's the Earth or Jupiter or whatever. So that would be, so if you have this, and you know things like the radius of the Earth and the mass of the Earth, you can actually calculate the escape velocity of the Earth. So you would know at what speed you would need to travel in order to balance out the energies over here so that your potential energy and your kinetic energy are the same, which would, in essence, allow you to be able to stay in orbit around, or stay in orbit around the planet. So that's normal escape velocity. I want to make sure I emphasize that because there is the more extreme case that I would go over here, and in this case, this is for, well, I'll let you, I won't spoil it right now. So now that we've got our escape velocity equation, what we're going to do now is we're going to take the extreme example with the highest speed that you can have it possible in the entire universe, which is the speed of light. And now we're going to make the assumption that the escape velocity is going to be the speed of light, c. So if that's the case, then I substitute c for v in here, and I get c equals square root of 2gm over r, which I'm now going to try and solve for r, and you'll see why in a little bit. But to solve for r, I'm going to have to move r over to this side of the equation, move c back over here. So in order to do that, I have to do a couple of operations to clear the way for r to come out, which means I have to square both sides of the equation first. So I've got c squared equals 2gm over r, and then I multiply both sides of the equation by r, and then divide both sides of the equation by c squared, and that's how I get r equals 2gm over c squared. Now, really, what is this? What does this r even stand for? This would be the Schwarzschild radius. This is what makes a black hole. Because you have to understand, a black hole is really a place. It's a region of space where light cannot escape. And so, what would be a region of space where light cannot escape? Well, it would be a region of space where you would have the escape velocity being the speed of light. So anything, let's say this is the surface of it. Anything above it, the escape velocity is less than the speed of light, so light could escape. But if it is the speed of light at the surface, once the light has gone into it, it can't come back out because it's nothing's faster than light. So in this case, every bit of light that goes into this object stays in this object permanently. And so that's what we call a black hole. So we now have the equations to not only understand how to keep things in orbit, just like the International Space Station, but how things can turn into black holes, and these are fascinating because we've actually seen a couple of them over the last few years, but also there are, in some of my more advanced videos, I'll actually mention how the existence of a black hole, while it is perfectly natural and it's perfectly fine, predicted by our equations, they lead to some pretty wild conclusions mathematically and logically that don't sit very comfortably. So what you're seeing here is like the first sign of the breakdown of physics. It's where we know, and all physicists know this, by the way, so don't think that this is like shocking to anybody. But this is the first step into a world where it's the frontier of physics, because how do you deal with a black hole? How do you take a black hole and mathematically make it work? And I'll go over a little bit more of that in a more advanced level video, but that's just to keep you on the edge of your seat there, just to think about it. This is where all of our mathematical understandings of our universe start to break down, because black holes are really that extreme. So that concludes the video on conservation of energy. Good luck in your studies, and may the force be with you.